Hello, this is the last part of the 2015 Oxford Pat. If I'd known there was only one question left, I probably would have put it on the previous video, especially as it's a resistor network. And usually these are really easy, although they're offering us 8 marks for this. So I'm wondering if they're going to throw a bit of a curveball in. We've got our resistor array they've drawn here. All the resistors are identical resistance R. So calculate the resistance between A and B. Right, so we can ignore C and D altogether and we can just add these bits up. So we've got R on that bit, 2R on that bit. That's going to be an R over 2. We've got an R there, so we've got a 3R over 2 on the bottom bit. So let's do our weird adding up of fractions that we do for these. So we've got a 3 over 2, well, let's put them as, I don't know, 4 over 2. We have to change all this in a minute anyway, and 2 over 2. So that's our 3 over 2, our 2, and our 1. Now, we want to get these now over a common numerator rather than common denominator. So we put them all over 12. So that is going to be 12 over, so that would be 8 plus 6 plus 12. 12 over 26, 6 over 13, 6R over 13. So that was an easy one to get us started on A. If a potential difference V is applied between A and B, calculate the power dissipated in the resistor between B and D. Right, so they're still sticking with this resistor network then. So if they're going from A to B, we split the PD according to the resistance. So we're going to have 2/3 of the voltage across here. That's going to be, 2/3 of V, because it's 2/3 of the resistance on that branch. So our power, which is V squared over R, is going to be 4V squared over 9R. Right, they're certainly not setting this up as an 8-mark question yet. Now we've got calculate the total resistance between C and D. C and D. So we're now going from there to there. All right, okay, I can see how this is going to confuse people. Yeah, right. Yeah, this is where you're going to be earning your points on this one. So, right, yeah, this is going to be tricky. We're going to want to redraw this diagram to make it a bit clearer, I think, because they have drawn it with A to B in mind. So we need to reimagine this by going C to D instead. And there's 2 ways you can do this. Well, there's probably more ways you can do it, but there's 2 ways that spring to mind. And hopefully one will convince you, because quite often people don't like redrawing these diagrams. Right, version number 1 of these is you can say any point connected by a wire is identical. So we could move C down to here and say, well, that doesn't make any difference because there's no resistance between those 2 points. It's still at the same, it's exactly the same potential when you get down there. In which case, if you redraw off of that, with that being C, it makes it a lot easier. If we put D here and C here, well, if you're going one way, we've just got that one resistor, which is this one down here between B and D. So, and if we're going the other way, we've got a parallel branch here, which has got 1 resistor or 2 resistors. And then we come into the other one, which is the branch with the 2 individual resistors. So that's one way of redrawing it to get it to look like that. And then we work out this, well, let's work out the resistance off of this as it is, and then we'll see. So that's going to be a half. That's going to be 2/3. So we want to add those together in order to get, so let's put it all over 6. So we've got 7 over 6. So we've got 7 over 6 and 7 over 7, and we're doing inverse fractions. So we're adding the denominators rather than the numerators. So that'd be 7 over 13R. Right, let's actually make that look like 7 over 13. 7 over 13R. Right, if you're not entirely happy with, let's just move C down there. Let's try this again then with thinking about potential, right? So say we're going to think about this as a whole circuit and what's actually going on. So we've connected up D and C. So we've put a wire around here with a cell in. So now we've actually got a circuit with some power going on. So what happens when we get down to C? Let's think about this in terms of potential. So let's draw out some stuff with different colours. So when we're here, all of this bit, all these wires, I'm just drawing over the wire lines, all of this, because we haven't hit a resistor yet, so that's all got exactly the same potential. And in fact, it's got exactly the same potential all the way around here once we've come out of the cell. So all of that is identical potential. Let's draw in some other potentials then. So what if we were at the other extreme? Let's go over to green. So by the time we've got down to D, all of this wire here and going back to the cell, that's all at our minimum potential. So the green line is low potential. Let's go back to the red bit. So the red bit is high potential. And we're always going to be moving from high to low. So let's take another colour. What's going to mix quite nicely with this? Let's do maybe, let's do a yellow. Hopefully that will come out. I'm going to use yellow on here. Now this other bit, of course, if we hadn't have gone through this resistor down here, then we'd have to go through one of the other ones. So let's ignore this bit between the two resistors in the middle here. Let's ignore that. So if we've gone through here, so we've dropped down to a sort of medium potential. We haven't got down to the lowest bit. We're at some sort of intermediate potential here. So we've got a medium potential there because we've gone through a resistor, so we've lost some energy, but we haven't made it all the way to D. So we've still got a bit left to use up. Now, by the time we've got to D, we've used up all the energy. So if we've gone via the yellow bit, we've only gone part of the way round. So we've got two ways really of getting to D. We can either go, let's change back to a colour that I can actually read now. So we've got a choice. We can go straight from the high to the low, or we can go from the high to the medium to the low. You can, because you can never go back up again. We can't gain energy and go from a lower potential to a higher potential. We're always dropping down potential. So these are our options for navigating around this circuit. So if we've started at C, then we've got two options. We're either going straight to D via the one resistor at the bottom. That's doing our high to low route. So that is our high to low route that we've got there. Or we're going the other way. So if we're going the other way, well, we've got to hit one of these two bits first. We're either going down the double resistor middle route, or we're going through the single resistor top route. Yeah, that is our only way of getting to medium potential. So we've got those two options. We're either going through here, gets us to medium potential, or we're going through there, which gets us to medium potential. Then when we're at the medium potential, our only way of getting to D is going through the branch at the bottom, the parallel pair at the bottom. So this is our high, that's our medium, that's our low. So that's another way of thinking about these. If you're struggling to redraw a resistor array, then draw in these potential colours. You're always dropping down each time you go through a resistor, and there's no way of coming back up again. So, I mean, this is what's stopping anything going that way on this middle branch, because we're at medium, you can't go back up to high. So everything has to be moving in that direction through the middle one. You don't have any choice on this. So if you're wondering, well, how on earth do I draw in this middle branch, which is quite often the position people are sat in when they're redrawing these things, yeah, they might start off. So say you had got to a position of redrawing it where you're thinking, okay, fine, you come out of C, you can go down to that individual one and then into D, or you could go up to or across to the left to the individual one, and then you could go into the double one at the bottom. So you might have drawn this bit, and then you're thinking, well, what do I do about the two in the middle? And you're kind of thinking, well, I need to sort of put it across here in some way. That's the sort of way the picture looks that you put it there. And that is the same picture. The thing is, you can only go that way through those two resistors. You can never go back the other way. So you don't have a route where you're going up, round there, and then down here, and then through there. That route isn't allowed because you're suddenly going from medium up to high potential. You don't have an option of doing that. You can only go down here and then up there. So you're essentially then limiting it to look like this picture here. So that's the thing that solves this confusion of where do you draw in this middle pair. If you've drawn it in there, well, it is still the same thing. It's not changed. This is why we can now move C round to here. Because if you're moving C to here, well, you've still got the same choice. You either go up that way through the top one, through that middle one there, or go that way. So you can see how we're piecing these things together. And I think the potential approach just works quite nicely of seeing what direction you can move through all of those resistors. Because as soon as you've got that, you've just got a choice at every junction of which way you can go, and then we can draw all of those options in. So hopefully that's made it a little bit clearer of how to redraw those those resistor arrays, because that's where you're getting your 8 marks from, I would imagine. I mean, the first two parts we saw, you can just write them down pretty much. They're so easy to do that you can't be getting more than, say, 2, maybe 3 marks for the first two parts. It's all going to be, you're getting 5 or 6 marks for the last part, and that's whether you can redraw those diagrams. But I like the other thing I like about the potential approach is it gets you thinking about what's actually happening in the circuit. What is going on here? How are we guiding the flow? What's happening to the energy? What would happen if you started plugging other things in? Plus, of course, remembering that they're drawing these lines coming out the side here. These are our connection points for connecting up other things to actually turn it into a circuit. Just having a resistor array is not a circuit. There's no energy source there. So connecting up C to D with a cell there, that is what's turning it into a circuit. Of course, we might have other things that are in here as well. Other components which are connected in various places. That's what's turning it into a circuit. We just want to analyze what's the effect of the resistor array on the current flow and the energy use and all of that sort of thing. So actually, I'm quite pleased I separated this off as a separate video because there was a lot to discuss in all of that. So really nice question in the end of thinking where you can get things to flow. But I expect, as I say, that a lot of people ended up in that position where they're thinking, oh yeah, we've got a resistor. We've now got 2 resistors which are weirdly connected across like that before going off to the other one. How do we reconcile all of this? And it is because we've only got flow in one direction through those resistors. That's why we can separate it off. Really nice question. Great way to finish off the 2015 paper.